Yeah, all right. So yeah, my name's John. I started off at RMC. I was a classmate of Dr. Morelli over there. And yeah, and after that time, I was signed up as a combat systems engineer for the Royal Canadian Navy. I went to the West Coast. You get to pick east, west, and I went west. And I trained on HMCS Calgary and served on the Regina. And yeah, then I did my time and I left and I went to go live in Vancouver, where I got hired by a company called McDonald Detweiler. And originally I was hired to work on a type of ship called an MCDF, which is it patrols the coastline. And then I got put on space station. And I started working on that, and I'll get into that, like what that was all about. And we were basically doing the operations control software for the arm that was going to be delivered and mounted on the ISS, which wasn't up yet. So I followed that project all the way from architecting key systems, developing, testing, and finally I went down to Florida for about a year to do the final testing with NASA. We shook hands, signed off the system, they wheeled SSRMS off, put it in what we called launch configuration, and then it's kind of like Indiana Jones. They put it on a cart and they put it in a room somewhere for the space shuttle launch, which was going to be a year off. So after that, I kind of had empty nest syndrome. I didn't know what I wanted to do so much, and people weren't really lining up to buy more space arms. So, I went to go work at a company. Let's see, I worked at a company called Mitel. Back in Ottawa, so it was telecom, so I was building systems operation control software for switches and other things. And then from there, I moved to Toronto, where I worked for Texas Instruments, and we were doing digital signal processor software. So like basically, they have tiny little chips that are pretty much indestructible that do anti-lock braking systems for cars, to chips you put on your mobile devices, to big chips which go into video cards. RTI was a big customer of ours. So anyway, we did that for a while. And then I had another existential crisis and decided to completely change things. And I packed my belongings, moved to New York City. And I worked on operation control software for the bank. And what that was is when you work in the bank, I worked for Morgan Stanley. And then around 2008, I was at Lehman Brothers, if you guys remember your history. So yeah, a week before the world economy blew itself up, I was on the trading floor at Lehman Brothers watching all the good things our software was doing. And then it did work, though. So it worked too well, I'd say. And then so basically, after that, then I worked for Barclays Capital, did stuff for them, and then came back to Ottawa with my wife, and we set up in Ottawa, and I went to work for a company called Thales, and they did system operation control software for the Army, and basically they were going to mount, they're mounting screens inside of armored vehicles and tanks and helicopters. And they all had to be able to communicate with each other. Surprisingly, they didn't do that at the time. So it was building that capability for the Army. And I did that for quite some time, and then I decided to become a consultant. So I got set up with the Canadian Association of Consulting Engineers, and up to today, I consult for the government on a variety of different projects. So I tried to give you the whirlwind tour of my life, and then there it is. So let's talk about the project I did 20 years ago. So hopefully I won't get tripped up too bad. I was going through my notes last night to try to get myself familiar with the old arm. So guide to the I'm not sure how we do. We don't do questions, or do we keep going? Okay, does anybody have a question before we get into MSS? No? Okay, all right, so here we are. The MSS stands for Mobile Servicing System. The big mission goal of this system was there was no space station. There was going to be a module from the USSR that went up first. It was called Zarya. And then from there, modules would come up, they'd be grabbed and attached to the overall structure as the system built up and built up. And what you needed is basically, you civ engineers out there, you need a crane. Unfortunately, it's a crane in outer space, so that's what MSS is. So the first piece that went up was the SSRMS, stands for Space Station Remote Manipulator System. It's different from Canadarm in that, well, two big differences. One, the joints, there's one extra joint. SSRMS has 7 degrees of freedom, Canadarm had 6. What that means, the big, with my engineering hat on, that means with Canadarm, you only had one solution to capture something, whereas with SSRMS, you had an infinite number. You could approach from the bottom, approach from the top. You had an infinite number of ways to approach your target, which was important because, you work in you don't want to hit the solar panel or hit the HAB module, so you needed a lot of flexibility. So there's SSRMS. I think it's on the HAB, and it's in its standby mode. So funny thing about space hardware, you don't turn this stuff off. You're on a 90-minute orbit to go around the planet. So half of that, you're in the sun, everything gets really hot. The other half, if you're behind the sun, you've got the planet and then the sun, things start to get real cold. So what happens is the SSRMS has an off mode, but usually it stays in a thing called keep alive, which means all the computers are down, but there's heaters. There's about a dozen heaters within the arm itself under the thermal blankets. It just keeps everything nice and toasty. So I don't know if you guys can read this, but basically the arm, it's symmetrical at the elbow. So you have, if you cut it at the elbow, SSRMS is identical on both ends. So you have the boom, boom A and boom B, Lee A and Lee B. Lee stands for latching end effectuator. That came directly from Canadarm. Basically all it is, it's a big bucket. If you see on satellites, I don't know if you see them, there's all these white squares with black dots on them. Okay, the reason for that is there's software that can, based on those dots, can calculate what its position is in space and what its orientation is. And then you have a capture pin. It's a standard, we have that standardized between the Japanese, the Russians, and NASA, and we're aligned with NASA. So so what it is, it's a pin with a ball at the end. And what happens is the Lee, it's a big bucket. You put the bucket over the pin. There's 3 metal cables that turn and wrap around the pin, and then the whole assembly's pulled back, which means it wraps on that ball, and that's how you capture something. So it goes over your target, and then with a thing like a lead, depending on what you want to do, there's a unit with 2 power ports. They'll go down, and either they'll supply power to the payload, or they'll provide power and data. So if there's a computer there, you can talk to it. And then let's see. Oh yeah, so the reason why they're identical at the elbow, SSRMS is designed. There were 2 other components. They weren't there at the time, and SSRMS needs to be able to move around the station. And what happens is that the arm, you put it down on a pin and you get power and data. Call that the slinky maneuver. What happens is then it detaches and it goes end over end like an inchworm, and then it goes to the next power unit, the next payload capture position. And then that's how the arm can move around the station. It can just inchworm its way around, and it can get to any part. So generally what would happen is it would inchworm its to a capture position. The space shuttle would come up, dock, and then the payload doors would open, and SSRMS would grab the payload, usually a module, and flip around, attach it, and you'd have some guys doing EVAs. They'd be like hooking up cables, tightening down bolts, and that's what we did. Briefly, the SSRMS electronically works on what we call functional strings, and at the time we had 2 functional strings, so a primary and a secondary, or redundant. And what happens is that in each joint there's 2 motors, primary, redundant. There's 2 arm control computers, one on each boom, primary, redundant. All the video units, there's double up on cameras, primary, redundant. And they're all in a line. So that was a bit of a design problem, but at the time, that's the way they did it. Space systems now, they're on what we call dynamic strings. So what happens is as the arm powers up, it'll decide, it'll go, okay, I'm gonna shoulder roll, I'm gonna be primary, shoulder yaw, I'm gonna be redundant, and it mixes it up. The reason that's important, because if you're always powering on the primary, you're never using the redundant, and it's kind of like a computer you never turn on, and then the one time you turn it on, it doesn't turn on. So it's like, because it's been quiet for so long. So it's like, so that it was the idea to get around that. They get around that now just by the mission planner saying, we're gonna do this operation on the redundant string. And let's see, and the stuff I worked on is inside, it's a workstation. Well, I have a slide for it. And it's in the, there's one in the hab, and there's one in the, what they call the cupola. And all the cupola is, it's an area that has a big, I don't know if you've seen pictures of the space station. It's big, it's got a mirror, like a window. You get a panoramic view of the Earth. And in there is the other, other workstation. And our software from MDA was the operation control software that ran that workstation. And what we would do is we would unsafe. We would do we did all the stuff at the higher level. So we would command the ACU to say, the astronaut, there's two controllers. One is a translation and one is an orientation. So if you want to put the head, the Lee, at a spot, you use one controller to move it around. And then if you want to change how it's approaching its target, you use the other controller. And our software would talk to the ACU, not the ACU, the software on the arm control unit called SAX. And we would and SAX did all the crazy math stuff, all what we called the reverse kinematic equations, saying like, okay, you have to go here, calculate what the joint angles are, and then it would. And it would go through that, and then we also handled things like safing the system, checking they could work, ARM can work in different modes. I believe there were 6 of them, but the one that's used the most, there's like it loads in a file and it just says go to this position, then go to this position. ARM moves very slowly, by the way. It doesn't move, and it doesn't move the way you would think it does. Like if you go into manual mode and you start doing stuff, the arm doesn't go like that. The problem is it's the big problem of being in outer space. If I go from here to here, especially if I have weight at the end, what do I have? What have I created? Like I have momentum, right? Like I'll stop and then the whole station will start like turning, right? So what happens is to get around that, the SAX software does the equations in such a way that if I want to go from here to there, instead of going like that, it goes like this. It goes like that. And then, so it kind of tries to counteract all its movements. So if it goes that way, it'll be doing movements in the opposite direction to try to cancel that out. If you go into single joint rate mode, SJRM, that's where the astronaut will pick which joint, and then they just move the joint. And that just works as expected. And you can get where you want in that position. That's usually used when the astronaut wants to make fine tunes to the position. They get the arm where they want it, and then they want to fine tune where it is. That's usually before they do a capture operation. Okay, any questions so far? Anybody? Yeah?
Yeah, just quickly, why use that cable system instead of, say, electromagnets?
I think, well, one, engineers are funny about tried and true, and that's the exact same system they used on Canadarm. Canadarm does the same, and the engineer, and it's a funny story, the company that built Canadarm was called SPAR. The lead engineer was a crusty old guy. He retired when I got there, and he liked to hunt, and he based the design off of a rabbit trap. So like to catch a rabbit, you'd step and it would catch its paw, and the Lee was designed exactly like completely. It was like a carbon copy of that, and it worked really well. So they didn't decide to do. But you're right, they have other systems that are more. So that was one of its first missions. I was buddies with a mission controller. Anybody guess what this is? Take a guess. No? It's an airlock. So that's the space station's primary airlock coming out of, I think it was Discovery. And SSRMS is moving it. So basically what you see, that part there, that big circle, that attaches to the station. And then that other tubey thing is what the astronaut comes out of. That's about all I know about airlocks, but like, that's an airlock. And then, so it did its job. Here's another payload. So this is the thing. This was the other big challenge on our software of how to capture something. And then we had two terms that we used a lot. There was active and passive backdriving. So the question is that when I put the Lee over that pin, whatever is attached to, what's it attached to? Like, that's always the big question when you're doing with space operations. Like, is it anchored or is it free floating, right? So if I'm bolted to this and I'm trying to capture something that's bolted to the same thing, it makes my life a lot easier as opposed to something's floating, especially if it's floating it's got some momentum and it's moving. How do I capture it, right? So in the case of passive backdriving, that's the case where I'm bolted to the same thing it's bolted. I'm trying to catch something on the space station and I'm attached to the space station. What happens is I go over the pin and then all the joints go limp. So there's no power on the joints. If you went up to it, you could just move it. And what happens is that the rabbit trap will close on the pin, the assembly will get pulled back, and then the joints of the arm, because it's 7 degrees of freedom, it'll just kind of mold around the pin and then latch to the target, right? So it's a really easy way to catch something. And then once it's latched, the joints get energized, they get powered, like the motors turn on, and the arm becomes rigid again. And then you go through capturing, like you put the power data pylons down, and then you can start talking to it. Now, in the case of active backdriving, that's different. Something's floating and you have to catch it. So inside the Lee, they also have a bunch of sensors called accelerometers, which measure the acceleration inside the bucket. And especially if you've captured something, it'll tell you, where your tensions are. And what happens is the joints are under power, and as the accelerometers are reporting their data, the arm's changing. Like the joints are slowly trying to, so if there's some pressure over here, meaning it's going that way, I'm going to slowly tug on it. And it's trying to kill its momentum and stabilize it, and then it pulls it in, and then once the pylons go in, it's captured. But at this whole time, all the joints are powered and rigid. This is very dangerous because if it's something like the size of this big bad boy here, the joints can't take that much pressure. So if you push too much in one direction, you'll damage it, or even worse, you'll bend the boom. And wow, if you bend the boom, you're in a world of hurt, because all the reverse kinematic equations I talked about, they all assume you've got a straight boom. It knows how long everything is. When you change any of that or any of the characteristics of the joint, your equations are useless. So, or you have to upload a whole software package to figure out to get around that. So, those were the most stressful missions on SSRMS. So as years go, we're building the station, and then a new friend shows up, and that's the MBS. So the MBS stands for the Mobile Base System. Part of the station, it was called the truss. Truss is just like a choo-choo train track that goes from one end of the station to the other. And it's the keel of the spacecraft, like it's its backbone. And while the truss is, so when you see pictures of the International Space Station, you see all these panels, solar panels coming out of it. Those are all hard docked to the truss. And what happens is you have this MBS, which just rolls up and down that truss, which is nice, because instead of having to do this inchworm operation with SSRMS, you've got the MBS, it just rolls down the tracks with SSRMS attached to it, and just takes it anywhere it needs to go, which is pretty handy. And then later on after that, SPDM comes around, and SPDM stands for Special Purpose Dexterous Manipulator. The idea behind SPDM, it's supposed to drop the amount of EVAs, so astronauts going out, because EVAs are incredibly dangerous. All sorts of things go wrong. Guy has the wrong breakfast, throws up in his suit and dies. Like it's just, it's just horrible, right? So anything could go wrong. This is basically, he's just he's a glorified double power drill that goes out. He's got these two arms. He's got a tool belt. He's got different types of equipment you can attach at the end of his arms, and he drills them. So he can go out if there's a new payload. He's got pinchers. He can move cables, and then the other arm can drill them down. And basically, the idea was to help with construction. MBS also has a thing called the, we call it the POA, stands for Payload Orbital Assembly. All it is, it's basically just a floating power cord. So it's a power module. So what would happen is SSRMS is going to pull something out of the space shuttle, and it's going to plug it into the POA. It gets to keep its heaters going. It gets power. It can get data uploads from POA if it needs to. It's like whatever the mission specialist, he's probably using via the POA to get the payload ready. So when the MBS is rolling down the truss and it's ready to take it off and plug it in, it's all ready to go. It's all powered up and it's checked out and ready. So SPDM. This one's near and dear to my heart because originally when I was I was sent from Vancouver to Brampton, Ontario to work on SSRMS. Once SSRMS was at a fairly mature state, I started working as a software engineer on all the software requirements for SPDM and the design. So that took about a year. It was about a team of 10 engineers, and we basically played the what if game every day of going like powering this guy up is way more complicated than the SSRMS, and then it's got two arms instead of one. However, you got to remember back there's a one controller, so the astronaut can only work one arm at a time. So how do you keep, how do you move one arm over here, and then the astronaut's paying attention, he puts control back to the other arm, and he karate chops the arm he just moved, which could happen, and then you've destroyed your equipment. So it had a lot of interesting challenges. The idea is if you see that he's upside down, but if you see his little head with his little beanie on the top, that's SSRMS can grab him from there and move him around like a power tool, and then he'll plunk him back probably on the MBS when he's done with him. So he's and there's also a roll joint at the waist, so the whole assembly can rotate. Anyone have any questions? It's always good to pause. Okay.
Either one of them, like, it always needs to be tethered to have power, or is there some energy storage on board?
No, there's no batteries at all. It has to be, the Lee has to be plugged into something. Yeah. And not only, and that was a big problem because when we originally delivered SSRMS to the Kennedy Space Center, we actually had the Zarya module there. And I was telling Jordan so back in Brampton, everything worked great. You know, everything, it works on my machine. The lab, it works beautifully. And then you bring the prof in and nothing works. It doesn't power on, everything fails. Right? And then, so everything worked great at the lab. We were like, awesome, we're ready to do integration testing with live flight hardware. We sent it down to Florida and we plugged it into Zarya and it didn't even power on. And it was just, and it actually shorted something out in the Lee and we had to repair it. Like it was just, and then we found out that the control document, the interface control document for Zarya had changed and it was much different than what was actually there. They sent a bunch of people there. We got a crash course in Russian, English, figuring out how interfaces work. And we sorted it out, took a couple months. And then once we figured out how Zarya was talking, we were back in the game. All right, so then we have, so this is a little more about, this is more about SPDM. Same idea, 7 degree of freedom. Yeah, a lot of cameras, so you can do. The other idea behind SPDM was they would want it to get it, like one of the requirements were pick it up with the SSRMS, and if you had space shuttle docked to the station, this was around the time of Columbia. What they wanted to do was do an inspection of all the tiles, the re-entry tiles on the bottom of the spacecraft, and just to check for damage. So that's another big role that SPDM had, would be looking for damage. And then they were even talking about maybe mission plans to repair with the arms if something was found, but I don't know where they went with that. And let's see. Here we have, so here we have, and I believe it's an EVA, and that's SSRMS doing part of an assembly mission, and I think it's for one of the solar panels that we had. So it's always interesting, and I'll get to it in the talk. Okay, I'm going to speed up a bit. The SSRMS doesn't work in on Earth. In 1G, this thing's too heavy to move. So don't think in a lab you'd see like the arm moving around doing this thing. When it was on Earth, it was taken apart. So you'd have like, that's the shoulder roll, that's the shoulder yaw, that's the shoulder pitch. And everything was done in simulation. So simulation would be connected to our operational control software and to SACS. And as the astronaut was moving it, you'd see like laid out, its guts were laid out on the floor, you'd see the joints move. But yeah, that was it. It was only, so it was one of those things is not only were we putting it up, it wasn't, the only time it was going to be constructed, like put together and actually tested out was on orbit, which is a terrible place to test stuff. So, yeah, so actually all the development that went into the operation control software and all the other software, probably 100 times more effort went into the simulation software and the testing rigs that we had to build to test this thing out. Okay, this is the cupola. So you have a beautiful panoramic view. I've been told by astronauts this actually makes you sick when you're try to operate the arm. So they prefer to use the HAB. So you have your 3 screens, your 3 monitors. Those go through the video distribution unit to the cameras. One's on the lead, 2 are on the boom, and you get a good look of what the arm's doing. And then you have your standard Lenovo laptop in the center, just plugs in. Every astronaut gets one, and right. And then we have there's the translation hand controller, and there's the rotational controller, and then this crazy-looking scary panel here is where you do your safe. The big red button under glass is the safe button. Call it the holy shit button, and then we have your selector, your joint selector, and then like what kind of mode you want to be in. Tells you what's safe, what's not, and then you get telemetry brought up on an overlay of how fast each joint's moving, where the end is, and all that good stuff. And that's the same thing, same rig, but it's inside the HAB minus the vertigo-inducing windows, and then and that's the controller. Okay, that's a diagram of it. This thing was kind of my bread and butter. Like if we ever got bugs from the system, it usually had to deal with this thing. And it's funny because if the astronauts had feedback if they didn't like the D&C panel, it was that took about a year to figure out how that buttons were arranged. Because once it was done, you can't change. It's not a virtual thing, right? So like getting that thing done. I just remember being in Florida, an astronaut was very angry about where a button was, and I was like, I don't know what to tell you. And then, so we have, and then there's also like a spin, like a mouse, one of those, I don't see them anymore, but it's like one big trackball, and that would, you can't have a mouse with your laptop, so it would plug into the laptop and allow you to play around.
Why can't you have a mouse on your laptop? Is that a space thing?
No, well, yeah, your mouse will fly away. And then, and then the other part, there's just nowhere to put it. You'd have to mouse on the, it's just nowhere, like you'd have to, I don't even know how you do it, off the DNC panel. And then, let's see here. So here is the simulation software, sort of an architectural view of it. The mission controllers would load into the local database. You'd have your graphics library. For the early 2000s, the graphics were pretty awesome. It's pretty good. We had the whole station. We had the SSRMS, and we had a mock-up, it was a live workstation, it was actually slated for a flight, and then we pulled it out with a lot of screaming and yelling at upper management to get it put into this system. And then, it's a thing for you engineers, like upper management, man. You got to deal with those guys. Sometimes it's not easy. Then you have your simulation models, kinematics. We put the live flight software in here. I can't tell you how many bugs we found in OCS doing this, like going through a mission. Just crazy bugs where someone would safe the system and that caused the OCS to crash because it was using too many cycles with the VDU. And I'm kind of running out of time, but it's an interesting how OCS didn't run on an operating system. It was the operating system. And what happened is we worked on a 50 millisecond or 20 hertz timer. And in the background, there was a hard called a watchdog timer. So it would start and it would give us 50 milliseconds to do everything we need. And then it would stop and we would have to hand over to a different board. And that board was in charge of the drivers, it would move memory around. It was part of the bus. The whole thing works under, it's called a MIL standard 1553B. It's just a standard, it's like TCP/IP, but it's used for weapon systems. It's used today by Boeing uses it heavily for its flight control systems and engines. So 1553, it kind of dealt with that. It was like your NIC card, basically. It had 50 milliseconds to do its stuff, and then it would come to us. So if we had to process 51 milliseconds, we'd break our watchdog timer. That's it. That would be a level 9 uninterruptible trap, and the whole thing would just freeze. So we had to deal with that. It had enough time to write a number at a memory address of what happened. So that's where we put in the debugger, so we could get a stack trace out of the software after it killed itself. And that's it. This guy was my best friend. And then that's it. This is kind of where we say goodbye. This is SSRMS and its launch configuration. What you have is a boom. There's a slide. There's a couple pins and joints. You take those out, and the whole boom breaks in half. And you can kind of slinky it up into a nice little square. You put it into its launch pallet, and then you drop it into the back of a space shuttle, and off you go. And then it was funny, it was before we left, late at night, all the engineers, we showed up, we took off this thermal panel, and we all took turns signing it. So we all signed the Canadarm, and that was it. That's the last I saw of her. Well, so it's been 20 years, and she hasn't broken down yet, so I'm pretty happy. So that's it. That's all I got. What's that? Oh, that's it.
We have some time for questions. Any questions?
Yes.
Can you speak a little bit more about that, moving back and forth? How do you even start tackling that problem?
Oh, some really smart guys. I think the one guy at Spar who did the reverse kinematics, he